So the idea of today is we will learn a little bit more about linear algebra with the agent. I don't know if this is the right pronunciation of this library. And this will be introduced by Joseph. And I will introduce, I will talk a little bit about threading using C++. So I think, yeah, it's like 36 past 9, so maybe we can start.
We can
Yeah,
restart.
feel free to.
Yeah. Okay. Can you hear me?
Yeah.
Good. Okay. I'll share my screen and I'll turn off my video. Okay. Now, do you see the slides and hear me as well?
Yes, we can see your screen, the presentation.
Okay. Good. Okay. Yeah. So so the session for today is about linear algebra for C++, and basically we'll be focusing on using eigen. So this lecture, I guess, is slightly different from the ones you've had previously, in the sense that this itself is not part of the C++ standard, but it is very important for a lot of scientific computations, applications that I'm sure you guys are interested in. And if you come from other languages, say Fortran or Python, they are sort of more baked into the language. So like Python, you have NumPy, which is very standard. But in the case of C++, as of yet, it is still not standard. Oh, okay. So James, I see James is here. So if you have any questions about yesterday's exercises, you can pop in the chat, or he can take over. But otherwise, I'll keep going. So yeah. So back to linear algebra. So even though it is not part of the C++ standard, if you use a library, it's not too bad. So yeah. So let's get going. So these slides were originally from Chris and Rupert, and I'm using them and edited them. Okay, so this is what I'll be going through. So first of all, we will discuss why we need a linear algebra library and what to expect from one, and I'll go through some of the particulars of the eigen library. Basically going through some of the capabilities it has in terms of matrices and solvers. And finally, we'll go through a demo together in solving a one-dimensional diffusion equation. And maybe we'll look at an exercise at the end where you can try to use some of the functions yourself. Okay, so what do we want from a linear algebra library? So the things that we want to do, well, it's used in a lot of applications in any form of scientific computing. Say you're solving differential equations, running any physics simulations, or say financial simulations, graphics, machine learning. These are all just linear algebra applications. So in case you're not clear what I mean by linear algebra, I'm talking about say vector and matrices manipulations, solving linear equations, or yeah, basically when you try to solve any linear equations, you're doing linear algebra. So if we use a library, what do we expect from the library? We would want it to, first of all, be able to represent different object types. So the most basic of all, you want your vectors and your matrices. So vectors are very simple. You just list them as numbers, but matrices have different representations. So you have your standard dense matrices, and you have some sparse matrices. So we'll go through a little bit more later on what these are. But so you have sparse matrices, and you can have special matrices like diagonal symmetric matrices, which can be represented behind the scene in a more clever manner, and in terms of operation, it's slightly different. And you want it to be able to operate on these matrices and vectors. So you want to be able to multiply, transpose them. And if these are, say, 3D matrices, 2D matrices, you want to be able to rotate them and do various geometric transformations. And finally, one of the most important things in linear algebra, like I mentioned, is to solve linear systems. So for example, in the form of AX equals B, so A is a known matrix and B is a known vector, and you're trying to solve for X. This is a very standard kind of system that we solve. Another kind of unknowns that we want to know about matrices is we want to know the eigenvalues and eigenvectors. So these are different solvers that we will require. This is the general class of objects that we call them solvers. So there are different implementations. So there are ways of factorizing them directly to solve them. So I've listed some of them here. And you have also indirect methods. So indirect solvers, which are when you have a very big matrix and you can't solve them exactly. So you need some indirect method to get you iteratively closer to your answer. So we call these indirect solvers, like conjugate gradient. Yeah, so these are the kind of capabilities we would expect a linear algebra library to be able to provide for us. And also, obviously, for different numeric types, because we are not just dealing with floats and doubles, we want to be able to deal with complex numbers as well. So these are the kind of capabilities we would expect. So I remember I used to write my own containers for vectors and matrices and operate between them. And in hindsight, it was rather dumb because there are much better libraries out there that I can just use. It will be much simpler, much easier to use. It will be faster, if more efficient, and much more accurate because it's been tested by various people. And also, it's a lot more expressive, so I don't have to rewrite a lot of content for different data types. So basically, don't reinvent what people have done. And this is a very popular kind of library. So I see, okay, Joshua asked a question about whether eigen uses last symbol attack. So it can. So I'll mention a bit more now. So eigen on its own, it's just header only. So it doesn't require any further libraries, but it can use an optimized library. So yeah, I'll just go through this. So if you just want to have a very simple application, using eigen can get you very far with solving linear algebra on C++. But if you have a bigger application that you want to, especially if a lot of your program is trying to solve PDEs, so a lot of fluid simulations would use PETSI, which is a very popular library. And you have your standard LAPACK, which is your linear algebra routines. So these are very standard, but also you can get optimized ones. These BLAST routines would be optimized by, say, GPU providers, and your CPU providers, say NVIDIA, AMD, Intel, they will each have their own BLAST library that you can use, which are optimized for that particular platform. And eigen can use these optimized libraries as well. Yeah, I'll talk at the end about how to link them. But in the most vanilla form, you just need to include the headers, and then you're set. But there are various things that you can tune to make it perform even better. I hope that answers your question. So just a little mention that hopefully, thanks James for the link. Right, so there are mentions of a draft that in the C++26 linear algebra and ND arrays will be included as a part of the standard library. And we can only hope that this will happen because right now it's a little bit messy. As compared to, so if you're a Python programmer, you'll be very familiar with NumPy, and a lot of these capabilities are so standard that no one even thinks about which library they have to use. So I've provided some links here about different libraries that you can choose from and what benefits they have. So very often there will be a trade-off in complexity, but if you want to say be able to parallelize them with MPI, then PETSI is a kind of beast that you want to be using. So let me get started on eigen then. So I like to think about it sort of like NumPy because it is easy to use. So it is header only. So like I said, you can just download the headers and you can use it straight away. So that means if it's not installed on your favorite system, you don't have to ask your admin to install it for you. You can just simply download it yourself and start using it straight away. So on ARCHER2, it's provided as one of the modules. So if you just run module load eigen, I'll just put on the chat, then the header files will be available to you. So if not, if you're using your own home local compiler, then you just need to include your path to eigen and you're set. And out of the box, it contains some optimizations for ARM and Intel processors. So it uses some SIMD instructions so that they're vectorized and basically they're optimized versions of some of the BLAS routines. So it also has a very easy to use interface. It has support for dense and sparse matrices, vectors, and arrays. I'll mention this a little bit more later. It's sort of like vectors, but then it helps you perform coefficient-wise operations a bit more easily. It also has support for some solvers. And yes, so if you want to download the library, you can just go to the website or you can just do an app install. Yeah, like I said, it's already available on ARCHER2. You just have to load in the module. So, okay, so let's look at the most basic thing that we can do, which is to write a matrix in eigen. So the matrices we're talking about are dense matrices. So these are matrices where we store every value, regardless of what they are, every value for the entire matrix. So first of all, we need to include the header eigendense, which is where all the information about dense matrices are. So to declare one is very simple. Just call an eigenmatrix double 1010. So you can specify the data type and your size. So this is a statically sized matrix. So this is similar to how you have an array, which you've talked about before. And also, this is just a template. So you can fill in whatever values you want here, and it will give you the correct size. So for these matrices, you can set the value. You can call each individual element and set the values. And then basically, as you can see, eigen provides a very clean, easy to use interface for manipulating these matrices. If you don't want to have a fixed size, set size matrix, you want to dynamically size, like you would want a vector rather than an array. So how you would do it is, rather than putting a fixed size in your template argument, you would just use eigendynamic. So so previously it's 10 here, but in this case you can change it. So here I've declared a matrix that's of 64 by 65, and then I can resize it after. So this is sort of like a 2D version of the SCD vectors that you guys have been looking at before in the containers lecture. So before you ask, I know that people might be interested in, say, a higher dimensional, say a 3D, 4D matrix, so in basically a tensor. So eigen does have some support for tensors with more indices, but the support is not really complete. So yeah, so you can try it out, but then there are other libraries that can do this better. They each have some pros and cons, so I would encourage you to look at them for yourself. But yeah, so eigen is really geared towards 2D matrices and manipulations for them. Yeah, so which in most cases in solving differential equations, that's what you want. So here's just some shorthand aliases that eigen has. So previously, when you declare a lot of these double dynamic, or say double 1010, it gets kind of tedious very quickly. So what you want to do is there are just these shorthands. So if I want to call a 3 by 3 double matrix, I can just call matrix 3D 3x3 int matrix, 3i. You can do the same with dynamically sized. So rather than having a number, you just have an x. And if you want a vector, you just call a vector. So these are just aliases that are provided that gives a shorthand for what you're declaring, the different types. But you can obviously declare more yourselves if you want to say bigger matrices. Right. So once we have constructed these matrices, what can we do with them? So here we have an example of matrix multiplication. So I have two matrices, A and B. So you can see that one is 5 by 10, the other is 10 by 2, so they can be multiplied. And if they're not the correct size, it won't work. So yeah, so you can see that I can multiply matrices between matrices, and I can multiply matrix and vectors as you would expect. Other standard operations like dot product, cross product, transpose, and setting values, again, like you would expect. Right, so as I mentioned, there's this thing called arrays. So arrays are basically a way to represent your matrix or your vector in a way that you are considering them element by element. So in this case, what you can do is you can set the values of a matrix to be the sign element of a sign for each element of another matrix. So you can see here when I use it as an array, I can do these operations where I'm just calling an element-wise operation on each element. But just be careful that these arrays are not no longer just vectors and matrices, so they don't operate the same way. So you can't mix them with vectors and matrices. Yeah, is everything okay so far? Yeah, again, if you have any questions or if I'm going too fast, just feel free to say it in the chat. Okay, so one thing that's very nice with Eigen is that, say, if you already have a vector that you've declared, allocated the memory for, now you want to use it as a matrix or an array, then you can just sort of overlay or have a view of this underlying vector as a eigenmatrix. So here I have I've declared a SED vector of 1,000 elements of doubles. I want to see it as a 10 by 100 matrix. So what I do is I call this eigenmap. So basically mapping the inherent the 1,000 element vector as a 100 by 10 matrix, which is this A eigen. So I feed in the vector. But if I want to do it with another view, with the same data, I can just call it again with a different layout. So yeah, so what's nice about this is that I don't have to copy anything. It gives me much better data access to the same memory that I have already allocated. Right. So all the matrices that we've been looking at before are dense matrices. So as I mentioned, these are matrices where we store every single element. But in a lot of cases, we have matrices with a lot of zeros. So in a lot of differential equation systems where you have, say, finite differences between the neighboring points, your zeros, your non-zero values are just very close to the diagonal, maybe with a very specific pattern of where they are. So yeah, if you imagine if you have a 100 by 100 matrix where all your values are along the diagonal with an offset of 1, then basically 97% of your matrix is just zeros. So it would be very inefficient to store all these values. So what we do is we store them as sparse matrices. So we just store the non-zero values and their locations, so their coordinates in the matrix. So if we want to manipulate these, yeah, so it's not just for efficiency, it's also sometimes that your systems are so big that storing the entire matrix as a dense matrix is simply impossible. You don't have enough memory to do that. And this comes from a lot of big physics simulations where your system is so big that it will just blow up your memory. So you want to deal with them sparse matrices then. So inherently, it's stored in something called the CSR, which is kind of how you represent the matrix. No, CSR. But yeah, so basically, to use these kind of matrix, you include this header now. Rather than item dense, you have item sparse. And it's very similar to how you would declare a dense matrix. You just call a sparse matrix with the kind of data type that you want. There are different storage options. So there's column major and row major, basically how you keep your data, whether you order them by column or rows. So this would be beneficial for when you're doing different kind of operations. There will be some performance difference, but that's something that you should experiment with and also understand what the algorithm is doing. So yeah, so here we have some examples of declaring a sparse matrix, a column major by default, and a row major, and a vector that can also be sparse. So, yep. Right, so how do we normally build a sparse matrix? So, because we only store the non-zero values, so what we normally do is we create a vector containing what we call triplets, which are just the coordinates and the value. So here you can see I have a vector of triplets. So these triplets are just I, j, and vij. So these are the elements and their positions. So I first construct a vector like this, and then I just call a set from triplets member function, and then it will convert M into the correct sparse matrix for me. So this is in general how you would set up a sparse matrix. And yeah, so this is something that we can try out in in the exercise later on, and you can try out these functions yourself. So what can we do with these sparse matrices? So like your dense matrix, you have your standard transpose adjoint, and you can operate between sparse matrices, like add them, subtract them, multiply them. But you can mix sparse matrices and dense matrices as well, and generally these they will result in a dense matrix. Also to mention, Eigen also provides some geometric transformations. So you can do your rotations, different sort of affine transformations. So these are included in the Eigen geometry header. Right. So on to the more important bit. So now we can talk about solvers. How dense does a sparse matrix need to be before we should switch to dense matrices? I think that, well, that's a very good question. Normally, depending on the kind of problem you're trying to solve, it's in you should be. Yeah, I don't think there's a very general guideline, but in the kind of question that you're trying to solve, you can see very quickly. But also that also depend on the system size. So for example, if you're looking at the yeah, so Juan gave a very good answer. Is that when basically yeah, the storage of your matrix starts to get the trade-off in space is no longer worth it in terms of the benefit that you get from the nice layout of dense matrix. So yeah, so for the same problem, as you grow your size, say if you're trying to solve a diffusion equation, if you're solving for just like 5 points, using a dense matrix makes sense because it's a very small matrix. In memory layout is completely fine. But if you're solving for 5,000 points, then it's completely the memory footprint of that matrix is too big to be worth it. so yeah, so there will be some sort of crossover point that, but they tend to be inherent in the problem that you're solving, especially with a lot of stencil types of operations or these finite difference operators. They very often will create very sparse matrices. So yeah, right. So for solvers, let us look at the most simple kind of system. So we have AX equals B, like we mentioned before. So A is a known matrix and B is a known vector. We're trying to solve for X. Okay, so eigen, I think actually eigen supports, doesn't use CSR. It uses a modified CSR. And I think that is, yeah, I can have a look. But it basically pads some zeros next to CSR. And I think it doesn't have a lot more other than that, if Juan is willing to check for me. But yes, we can get back to that. So yeah, so we're trying to solve this equation here. So let's look at this example. We have an A. We just construct A this way, and B, your vector. And here is the line where we solve it. So normally when you solve these equations, you don't just directly solve them. You normally decompose them via one of the many methods and then solve it. So these decompositions have a few benefits. They can, say, improve stability, or they can accelerate further solvings so that you can reuse them. So the two steps are visible here. So you can first decompose and then solve with your right-hand side B. So you can actually save this object, the decomposed object, and then solve it with various multiple right-hand sides. And there are different kinds of decompositions that it supports, that eigen supports. It's not the most comprehensive, but it's the standard ones, like your LU and your QR decompositions or factorizations are there. And each of them will have different requirements on your matrix, for example, whether it's a Hermitian or symmetric or various different properties. They will have different requirements, and depending on the decomposition, they will have different reliability and speed and optimizations that's been implemented in terms of using optimized routines. So you can look at this link to check which decomposition is suitable for your matrix. Oh, wait, so this here is just basically showing the line where the solving happens out of all this. Just to point you there. That's it. Okay, so just to mention some other solvers that it's capable of doing. It can find singular values and eigenvalues, eigenvectors. So these, each of them have the examples I've given have different properties, and some of them requires, say, for a self-adjoint matrix, it can find the eigenvalue, and this one can do more general complex matrices. But there will be obviously a trade-off in speed. And again, you also have sparse solvers, so basically solvers for sparse matrices. So for these ones, you feed in a sparse matrix rather than a dense matrix. Okay, just have a support. So next, we have these solvers, which are called iterative solvers. So when you have a very big matrix that's very, well, normally very sparse, so you don't actually want to fully decompose them and solve it directly, because it can end up with a dense matrix that you can't deal with, or sometimes there will be instabilities that occurs in direct solving. So you need to iteratively solve. So basically, you keep multiplying by the matrix A to iteratively get closer to your solution. until you're satisfied with the tolerance. So for a lot of these common methods like conjugate gradient or some variations of that, it's also supported. So you don't have to implement it yourself. Right, so as a general note, Eigen by default does a lot of checks. So you definitely want to, well, when you're testing, it's good to keep them on, but then when you actually run production code, you will want to turn off debug with the macro and then turn on optimization. And as I mentioned before, and James has posted a link, that you can link with an external BLAST library, like your InterMKL or your OpenBLAST, by enabling a macro so that it will use the optimized routine behind the scene. Okay, so now let's actually go through a demo of using some of the functionalities in Eigen. So what we're trying to do here is a very simple diffusion equation. So I hope it's clear what diffusion means and what this sort of system is trying to tell you. So basically how the system evolves in time. Yes, yeah, so how the system evolves in time depends on the Laplacian or the second order derivative across space. So if you imagine a high concentration of, say, temperature or concentration of gas would diffuse to a lower concentration. So physically, this is what's happening. So we will solve it through what's called the explicit method. So basically what this means is we have an initial state and we can evolve that state with a matrix A to get the next state, n+1. So n is here is a time. So if I want to go to the next time state, I multiply by a matrix. So here I want to use a dense matrix A to represent my evolution. So I keep multiplying A to get my subsequent states. So if we're happy with this equation, then let's try to discretize it so that we can convert the differential operator to a finite difference operator. So what I've converted that into the equation previously is that, okay, so now time, the evolution in time is going from Tn. So on the right-hand side, it's just Tn. And it evolves to Tn+1. So this is the next time step. And you can see that I've also changed the Laplacian into a finite difference. So you can see the next time step depends on the neighboring points. So from I depends on I-1 and I+1. So it's just the neighboring points. So that's how you discretize your differential operator. So we can recast this form into a matrix equation. So I hope this is clear. If it's confusing, I can spend some more time explaining this. If not, yeah, you can look at the slide to try to understand it better. So I can recast it into a matrix form where A is now this matrix. So what this is that, so you can see that on the diagonal, it's very close to identity with some mixing with the neighboring points. So this is how it evolves. So through each time step, it will mix with the neighboring points to get you a new time step. Okay, so I think it would be good if I share the code. So I have a site for code, but I think maybe I'll just show my editor. It'll be a bit easier. So the code is available on the GitHub. It's on exercises and Eigen. So I'll be looking at this explicit CPP here. So if you cloned it onto Archer, you can try to run it as well. So let me share my editor. Okay, so do you see my editor? We need to load the module first on Archer. Yes. So to compile this, you need to do module load eigen, which I have posted on the chat before. So I'm just running this locally because there's a little script that I have in Python that I can use to animate some of the results that we see here, and ignore the errors here because I didn't configure it properly. Okay, so this is explicit. So the explicit method. So what do we do here? So there are different parts. Maybe I'll share my whole screen, or maybe I don't know. Okay, so previously we have the right-hand side has two things. It has the matrix A. Matrix A. So here I'm setting up the matrix A by I first declare a vector of an n by n size. So n is the size of the 1D field that I'm trying to evolve. So I have an n by n size matrix A, and I map it. So this is one of the methods I mentioned before. I can look. I have a view on top of the inherent memory that I have allocated. So I put this memory in, and I view it as an n by n matrix. Eigenvector xd. Oh, so for this step, I'm not actually using this as a vector. This is just, as you can see, this is n by n size. It's not just n. So it's a vector that I'm allocating with an n square size. So later on, for the actual vector, I will be using a vector xd. So yeah, so as you can see, this is a matrix xd. So this is A. This is the matrix. Okay, so here I'm setting up the matrix A. So if you remember, it's the matrix that we've seen before with almost 1 in the diagonal, with deltas on the side. So I set it as an identity first, and then I basically do these manipulations to get an offset. So okay, let me just run this. Yeah, I've also included a makefile that you can just run. Okay, so I've asked it to print out what A is here. So as you can see, this is the matrix A that we get. So this is like the one that we've seen in the slide. This is what evolves our type. So you can see it will mix the neighboring points. Okay, so now we're setting up. Is it too small, or should I make it bigger? Maybe I'll make it bigger. Right, so next we set up B. So B is just an eigenvector xd. So it's just a size n vector. So we want to set it. So I want to set the initial condition here to be a step function. So it's 1 in the first half and 0 in the second half. So this will just give us a good demonstration of whether our model is working. So for each time step, this for loop, what I'm doing is I'm just multiplying A in each subsequent step. So this is iterative. Well, this is iteratively progressing in time, evolving in time to get my new solution B. So as you can see, this is a matrix equation. I'm just multiplying A by the matrix A by the vector B, which is Tn. So I'm saving this to a file that I call this. So let's have a look at what that is. The first 5 lines. Okay, so I start with 1s at the start and 0 in the second half. And then I have, as it evolves, you can see it starts to spread out to the second half. And I have actually made a little Python script to demonstrate what this does. So if I share my whole screen. Okay, now you see my whole screen. So I'll just change the file here. Okay, so this just reads in the result file that we've created just now. As you can see what's happening here. So it starts with a step function, and then it starts to smooth it out by the matrix A in each subsequent time step. So this is just a very simple example of how we would solve this diffusion equation with an explicit method. And all you can, so you can see here, you just declare a matrix, an eigenmatrix, an eigenvector, and you keep multiplying them, and that's it. That's your system solved. Okay, so let me keep going to the implicit method now. Okay, back to the slides. Right, so sometimes when you solve explicit methods, there are actually very bad instabilities that you can encounter. So if you want to read more, there's a link here. But basically, depending on the actual matrix, it can sometimes give you very wrong answers, especially if your step sizes are too big. So you are very constrained in terms of how far you can go. So it's better to solve them with what's called the implicit method, which is basically you have your system now with your tn+1 as an unknown, and your differential operator on your left-hand side, and you try to solve for tn+1. So previously A is on this side, now it's a different A, but it's multiplying the next time step. So basically it's just discretizing your differential operator slightly differently, basically putting things on the left-hand side. But now you can see it's a different A. So this might look very similar to the previous equation, but it's slightly different. Basically, some of the signs, I think, these signs are different. And you can see the matrix A is slightly different as well. So previously, this is minus, this is a plus. So basically, you flip your sign and you get your implicit matrix A. So, right, so rather than just multiplying the next time step, to get the next time step, what you now need to do is you need to solve for tn+1. Right, so let's go back to our code. Yes, so now I have the implicit version of this. So you can see the start is very similar. You set up your matrix A as a matrix XD. So, okay, so I didn't do the step where I set up a vector this time. I just straight up called a matrix XD. And then you set your A up in a similar way, and then give it the same initial condition with a step function. But now I'm trying to solve for this tn+1 for the next time step. So rather than just multiplying, what I'm doing here now is, like the example that I gave you before, you do a decomposition and then a solve. So again, B is your right-hand side, and you're trying to decompose your A here to solve for this B. And again, for each step, you just try to solve for the next B. Again, I save it to the file, and if I would just run this, right, you can see this A is slightly different. Now you get these minus signs, and this is previously smaller than 1, now it's bigger than 1 on the diagonal. So, right. Let's have a look at what this is. Okay, this is like messier, I guess. But you can see again, it starts with a 1 and zeros at the end, and then you can see it starts to leak to the right. And these are just like numerical precisions constraints. So right, so if you again look at how it evolves basically very similarly as you would expect. So just change this. Oh, I need to share my whole screen again. Yeah, and if I just run this, as you can see, it behaves basically the same. Well, it has this yeah, as you would expect, it's just a different formulation of the same problem. So this is how you solve it. Okay, so now that I have demonstrated how you would do it for the same system using the dense matrix representing the explicit and the implicit method, I think it would be good if you can try yourselves how you would implement the explicit method using dense matrix. So previously here in the dense matrix explicit case, these are all dense matrices. And they're constructed, so you can see these methods are how you would access a dense matrix. But if now I want to use a sparse matrix instead, because so in this case I was using a 20 by 20 matrix, it's not very big, but if I want to do a much bigger matrix, perhaps I would need a sparse matrix now. So maybe I'll give you, I will come back in say 10-15 minutes, say 15 minutes, and then we can have a look through how you would implement it. So maybe you can just change in your explicit.cpp file the appropriate lines to make the matrix into a sparse matrix. And don't forget that you need to include the right header files. And if you remember, this is how you fill a sparse matrix using the triplet method, and then you just set from triplets to construct your matrix A. So let's say we'll come back at 10:40, and then I'll go through some of the steps in the sparse matrix case, and we'll have a break after that. Yep. Right. So it's 10:40, so I guess I'll just quickly go through the implementation of the sparse matrix explicit method. So let me share my screen. Right, so like the hints that I gave you, so basically you just need to change your include to include sparse, and yeah, so this is one way to declare a sparse matrix that's n by n size, and here is what's basically been changed. So you have here, so I declare a vector of triplets, and this fill.reserve basically tells the vector to reserve that much size that we want to fill later on, without actually allocating or without actually using specifying what's in there yet. So here you can see, just like the explicit, I have these lines to make my matrix A. So just one thing to note is that, so you can see here, as I fill them in, there will be duplicates. So if you see these two lines, I'm filling I plus 1 and I plus 1 and I. So what happens then, if I have duplicate entries, is that they will be summed up when I run the set from triplets. So if you read the documentation, it will tell you exactly that if you have different lines in your triplet vector for the same element, they'll be summed up. So yeah, so I push all of them into the vector, and then I set from triplet, and then I construct my vector A. So if I just right, I'll just run this. Right, so it's very similar to before. This is the matrix A, but I guess one thing that's different to point out is that this matrix A now, yeah, you can see that it will also print out the actual representation in the CRS form. So you have the actual inherently how the data is stored. So yeah, so if I look at it again, I'll just change this to sparse. I'll share my screen. Yep, if I just run that. Right, so again, what you expect. So because this is just the same as explicit .cpp, except that my matrix representation is different. So yeah, that's really all I want to go through. And so yeah, so if you want to keep looking at the material, it's all online, but then otherwise, the next session will start at 11:30. Am I right, Juan?
Yeah. The break is from 11 to 11:30. Is that the question?
Mm-hmm. Yeah. So I guess I'm this part of the lecture is over, but then you can keep trying the different methods and in the exercise, and if you want, you can also try to change the sizes up, and if you can run it locally, because I know that on ARCHER2 you can't run the visualization with the Python. So yeah, I encourage you to play with it until 11 when you have a break, and then the next session will start at 11:30.
Yeah, also, if you have any questions, please feel free to ask. What the idea is, at 11:30, we will start with the last part of this course is threading using C++. So we will see that, and then hopefully at the end we will have some time for final questions, exercises.
Yeah.
So I wonder if you can see the slides, and also is the audio okay? Because I got a notification that my internet is not that good, so I'm not sure if it's Wi-Fi sometimes is a little bit not good in my flat. Okay, in case that you notice that the audio is not okay, please write that in the chat, and I can, I'll figure out how to solve it. Okay, so here the last part of this course, we will talk about threads. So C++ threads. Okay, so let's start. So we will see introduction, creating and joining threads, passing arguments to threads, and synchronization. I see that there is a issue. The slide that I'm showing now is says overview. I'm not sure if sometimes is could be
maybe you can refresh your browser.
Yeah, I think sometimes it's the browser that it gets stuck and you need to reload it. Cool, no problem. Yeah, it happened to me sometimes when I join other courses. Okay, so yeah, here we will talk about threads. These threads are mainly, so you may know, for when you want to parallelize an application inside one moment, forgot to. Okay, so this normally happens when, what happens? It's like when you want to parallelize an application using one node of, for instance, of ARCHER2. If you want to use more than one node, you would need to use MPI or any other parallel library, not threads. Okay, so here we will talk about C++11 threads from the C++11 standard. That is an API for multi-threading programming. The functionality is similar to POSIX threads. I don't know if you handle threads using C. You may be familiar with this type of threads. The difference here is like we are using a object-oriented interface, and also are based quite heavily in the Boost threads library. This is portable. Nowadays is available in most compilers today. And the concept here that each thread is a C++ object. So when you create the object, you know that the constructor is called. So in that moment, the thread is created. There are some synchronization features that we have available, like mutacies, condition variables, C++ atomics, and also we can handle threads like task using async futures promises aspects of the library. So to create a thread, the idea is that you have your code, you are in the main function or in any other function, and when you create an object of the class std thread, you will create a thread that will execute in parallel with the main, let's say the main thread, that is the program, program of the process that creates the thread. Normally, when you create a thread, what you do is you send a function to be executed by the thread. That could be normally you send a pointer to that function. So it could be a function object, lambda expression. There is a note there that is you cannot copy a thread. To be honest, I don't see much why you need to copy a thread. A thread is something that you need to do. So you create the thread, you tell the thread, okay, execute this function. That's it. I don't see that much the point of copying a thread. So please don't do that. Well, anyway, it's not possible. So joining threads. This is if you may be familiar with the MPI that when you at the end of the execution, you can call MPI wait, that waits all processes, all MPI processes to finish. Here is somewhat similar. The thing is in the main, let's say you're in the main thread and you create a new one. So in order to wait this new thread to finish, you can call thread.join, and this function, the function join, will wait until the thread is finished. Here we have a code, hello world function pointer. So you see that we are using the library, the standard library, the thread, and you see that we have a function called hello. This is the function that we will execute in a thread. So you see that we have our the main function that you can consider that has let's see the main thread, and at the beginning in std, let me see if I can. Yeah, okay. There we are defining a vector of threads. So what we are doing is we have a for loop. In our case, we will create five threads, but also you can choose For instance, it was a question that here in the when main is execute, we don't have any parameters, but you can include parameters here, and when you execute the software, you can say, okay, you can send as a parameter the number of threads. When this is executed, depending on that number, you can execute 5, 6, 10. And you see that here thread pushback is that you are adding the thread to the vector. And here when you create the thread, when you create it, you pass as an argument or parameter the name of the function, that this is hello. You see that the function is the return is void, because when we create a thread, we don't get a return value. So we just execute the thread and that's it. And at the end, before finishing because if you finish a main without waiting to the threads to finish, you may interrupt the execution of the thread. So what you do is, this is a fancy way of going through this vector. This is similar in other programming languages like for each. So for all the elements in the vector, you call thread join. So you wait to the thread to finish. And once that all elements are finished, you can finish with a return. Normally, but this is like a more, would say, style, or maybe to meet the. I see that in C++, when you compile this piece of code, is not complaining. But what I will do, if you return an int, I will finish this body with a return 0, for instance. Normally 0 is like no, didn't happen any error. Why you are, because you may wonder this return value, where is it? When you execute the software in the terminal, you can check the value that has a return, and you can check if the execution of the software has been okay or not. Any questions so far? Is everything clear, more or less? If so, I will continue, but I mean, please ask us as many questions as you may have regarding threads. There is a question that are the thread IDs are sequential. I would say no. I think you get a different number. There is a possibility that when you create a thread, you can specify the thread ID. That we will see that. Well, actually, let me. No, we will see later that you can specify the thread ID, but normally no, you don't. I would say that is not sequential. Or to be honest, I'm not pretty sure on the answer. But what I is that rather than getting 0, 1, 2, 3, you get a different number. So it's not. I would say that is not. It's not clear. It's not defined if a thread ID are sequential or not. I can have a look at check later. There is another question about, can you explain what threads pushback is doing again? The thing is, here you have a vector of threads that is empty. So here you have created that vector, and what you are doing here, the vector is called threads with the S. So what you are doing here, threads dot pushback, you are calling a function or method that is inside this object that is a vector of threads. Pushback is you are adding to the vector this what is inside this bracket. That this is the object, well, a thread, object thread, and this is the function that this thread is executed. So pushback is adding an element to the vector. Cool. So let's continue here. Okay, here you can either, the first choice was to define the function here. The second choice is also you can, in the same, you see here that as a argument, you can define the lambda function. This is possible, but I would say my concern that, or this is like rather more my opinion, that this is more readable than this other one. So for instance, because you see that here is sent hello, and hello is here. You can use this one, and they might be some occasions that this use would be better, but I find it personally, I find it more readable, this choice. But this is to show you that this is also possible, or this is made, for instance, if the lambda function is short enough, you can include here rather than. This is regarding the thread IDs. So when you execute a thread, you can call get ID on a you can get the thread ID. This is an arbitrary. It's mentioned here. If you want a sequentially number thread, you can, when you create the object, the thread object, you can tell, okay, use this number, this ID rather than this other one. Before we have seen that we have executed hello without any arguments. But here, for some, we want to execute. We want to execute the function hello, and we can the following arguments are the values of the hello. So here in the when we define, when we create the object thread, that the name is my thread, we have 3 arguments: the name of the function and the 2 arguments, x and y. And well, you wait by my thread join, and then you will get this print. This is important here. This mentioned that this is copied by value. So A and B, well, I think, but inside the hello, if you modify X and Y, or A and B are not in the main body, this will not be modified. Also, if you want to avoid, if you want to pass by reference rather than by value, you can do that. So for some reason you need to modify X. So you send, there are 2, one argument. So my thread will have the object or the thread. My thread will have 2, will have a hello, and pass by reference, you can use that, and then when you print, this will print 10 rather than. I will see if this will be. Yeah, later I can show a sample later. Okay, here we were talking about synchronization, because at the moment, before we have a user thread, and in the last case we have modified a value. But imagine that you have this class wallet, and you have an integer that is the money that you have. Use maybe a floating point, but let's say that we can only have pounds, say coins of £1. So in that case, okay, integer is the. So you can add money to your wallet, and you can execute it as that function. The danger here, well, the thing that could be tricky is imagine that you create 2 threads or more than 2 several threads, and you add money at the same time. It could be the case that you are updating the variable at the same time. So it could be a race condition. That means that this will not be maybe the quantity of money will not be accurate, because one thread could have a value 0, or let's say that both threads could have in cache the value 0, and when let's say that one thread adds 20 and the other thread adds 30. So when you save that, you can save here 20, and then when you save here 30 rather than 50, rather than the addition. So this is called a race condition, when you modify the same when the same variable could be modified by 2 or more threads, and you don't control that. Ways to avoid that: here we can use a mutex. That this is to protect updates to serve variables. So here in the class, you can declare a mutex, and you see it's quite I would say easy to because what inside the mutex, normally you declare that, and you use lock and unlock, and inside you do the update. So if let's say that there are several threads, if the second thread use mutex lock, and this mutex has been already locked, you will get the thread will wait here until the other thread execute unlock. Don't know if that makes sense. Let's say this is like when you are using maybe the sample is not but a public toilet, that when you enter, you lock the door, and you are there, and other threads need to wait in the door up to when you finish, you unlock the door, and another thread, another person could get access to the toilet. Okay, here this is, for instance, if you use C, this is like I would say the normal way. Normally you use mutex lock and unlock. In C++, and now in this, like if you use this pattern of resource allocation initialization, you can use std lock gar rather than let's say the original or standard lock. That means that when the lock is out of scope, the lock is the mutex is lock is released, because the thing is when you execute a lock, you should always remember to unlock. Otherwise, this will be always locked, and there could be like the program will never finish. Or if for some reason here inside that is an error, this mutex will be always unlocked, and this why they said that that could be a little bit tricky. So using a gar object, what you do is okay, you have here again mutex, but rather than unlock, you use std lock gar. Here yesterday we saw a template std mutex. So you see that you don't need it to unlock. So when this is called here in this scope, when it goes out of scope, the mutex is unlocked. Yeah, there is a question in the chat. Is what happens in a thread tries to modify an object that is unlocked? It just waits and try again later. Yes. So yeah, exactly. So all the threads need to use the mutex. If the mutex is locked, the thread waits until this is unlocked. So that's the idea. It's like a kind of like a kind of a barrier, kind of a door. If the door is closed, you cannot enter to. This is also quite interesting. I explained before mutex, the mutexes is normally you use them when maybe here is clear. Okay, here we are updating a value, but imagine that you need to do more operations. You need, for some reason, you need to update a file and change the location of the file. You need to do several operations. In that case, I would recommend to use either lock unlock or use this lock guard. But there are some cases that is only, for instance, in the wallet, we only take carelessly of the amount of money that we have in our wallet. So you can use std atomic. That means that the operations that you do to that variable are atomic. So when let's say that the variable will be updated or could be updated only by one thread at the same time, cannot be this is for integers, and this is floating point support. This will be in the C++ 20 standard only. So atomics, exactly. If you use an integer, you can use it. But yeah, depends on the standard. If you're using a later standard, you can also use a floating point. If not, you need to use the previous techniques that we have seen before. So this is the way of, so you declare the variable rather than integer and then the mutex, etc. You declare std atomic and you say, okay, so int. Now I understand why the was in integer rather than float in the previous examples. And you see that you execute this operation here is safe. It's called when you see, maybe you see some libraries on the internet that this operation is thread safe. This is a thread unsafe. So this one is thread safe. That means that you can execute this class in parallel using several threads, and money the quantity will be consistent. Yeah, this is what is about thread safe or unsafe. Here there is you should be careful. You should choose which. Okay, in my previous class, it's easy to see that, for instance, money is a variable that could be updated by several threads, and you should keep the variable, let's say, thread safe. But what I would recommend, or not use a mutex or use a lock guard when needed. So don't use it for if there is a variable that you know that will not be updated by several threads, or there are some functions. For instance, when you use print cout to print a value on the terminal, I don't see much the need of using a thread, for instance. So a thread. I don't see the point of using a mutex unless that you want, for some reason, to do some debugging and you want to print something in order. The recommendation here is if you don't need to use a mutex, don't use it, because otherwise the use a mutex is a little bit expensive in terms of execution time. So if you use a lot of mutices, the performance could be bad. It happened to me. I remember a while ago when I was using POSIX threads, I was using a mutex to update a value, and my performance was not good at all. And we discovered that we were using a mutex, and we could get rid of that mutex because we were not updating the same, all threads were not updating the same value. For instance, if you are doing well, now reduction is implemented, but imagine that you have a vector of 8 elements and you have 8 threads. If each thread updates one element of the vector, you don't need to use a mutex. I think my mistake in the past was that to update the vector, I was using a mutex. So the performance was a little bit, was not good at all. But we discovered that, we did some profiling, and we thought, okay, there is no need to use a mutex, so that's why. Okay, there are two interesting questions here. Do you have any idea of? Okay, there is a question about the C++11 atomic overhead compared to OpenMP atomics. I will say I'm not 100% sure of my answer, but I will say that these are similar. In the concept is similar. Is you have a variable that is atomic, so this variable cannot be updated by at the same time by more than one thread. So if let's say that it keeps control when several threads try to update that. That's an interesting. I will say that behind the scenes, when you compile the code, I would say that it's the same, but I'm not 100% sure. If I had to answer, let's say that I am in an exam, I need to answer, I would say that yes, must be the same performance. There is another question that is, are there any guidelines to when atomic operations should be used in place of logs? The idea here, for instance, in the previous class, in this example, I would use atomic. Why? Because it makes things easier. Here you are only updating a variable. So using you can also use a log, but it's not, this, for instance, this piece of code is more readable, and you don't need to worry that much about this atomic operation. At the moment that, for instance, you need to update or to do like a more, what I said, create a file, or is let's say that the operation is more complex. In that case, might be worth using log or log guard. Yeah, this is this is another point because atomic in C++11 is for integers. If you want to use this standard and use a floating point number, you will need to use log rather than atomic. Also, there's a comment in the chat saying that this is compiler dependent and hardware dependent. What do you mean? The performance of the I think that I would think that the atomic. I'm not sure if this is related with your previous question. Atomic is translated the same when using. Yeah, could be related with the compiler, but I would say that the translation is similar, or maybe, yeah, could be. I think could be depending on the compiler. I would say that the translation to when this is executed will be similar because they have the same, more or less the same features. But it's a good question. I will have a look later on, find out more about that. But yeah, that. Okay, talking here. Well, this is like the end of this part because the threads is 2 lessons. So we will go to this one that this is further topics, and this is also a little bit of kind of discussion of also like because before has been mentioned about OpenMP, and we will do, well, not comparison, but you may wonder, why do I need to learn about C++ threads when I can use OpenMP, or the other way around? If I use C++ threads, why do I need to learn about OpenMP? So the overview is we will see the STD async and features, parallel STL, I said the C++ threads and OpenMP. So async is a way because you have noticed before that when we execute a thread, there is no direct way to return a value for the from the function of lambda that the thread executes. There is a way to to get that this using passing an argument by reference, and in that case you can update that value. And also another way is to use STD async and features. And also it said that it returns the future object, and also calls the get function of the feature blocks until the value is available. Also, you can handle exceptions. We will see here an example now. Okay, so this is an example of using async. You see that you have here we are using another function that is well, this is a simple one, but this is for the example. Addition, you have 2 integers and you return the addition of these 2 integers. So you have a main, you have these two values, A and B, and when you call std async, the parameters are the name of the function and the A and B, that are the numbers that you want to, and you save that in well, this is like a std future template, and that the value is int. Also, if you want to make your life easier, you can use an auto, and you don't need to worry about it. But this is in case that you want to specify the return value is that one. And there, if you want to print the value, you can execute the object. So dot get, and the value will be printed when this is when the execution of the thread has finished. I mean, this thread is quite fast because this is just a return. But imagine that for some reason the thread do a connection to a database, do a join query, do some calculations, blah, 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 and might take longer than than that just a simple operation. So that's why you need that like to wait until the result is available. So here they said that it's like with this you can use synchronous of execution if you use the data parameter. And yeah, the thing is sometimes yeah you may get some delays with it, but normally I would say that this is normally, for instance, if you are using if the node is executing other applications, or this depends on the, I would say that it depends on the operating system. If when they say that okay, execute this thread, don't execute this thread. Also here we are learning a little bit about the STL, that for some algorithms we have a parallel versions. This is not entirely true. They said that part of the C++ 17 standard. They said that that is not yet available in most standard library implementations, but nowadays is mostly available. So this is not entirely true. This is, I think it was in previous versions of GCC, but now it's other compilers. I think now it's widely available. And you can execute the STL function. You can execute it in sequential, parallel and vectorized, or only vectorized. That this is added in the C++20 standard. I think it's better to see an example. The example is you have a vector and you want to short the vector, so you use std short. If you don't specify anything, you use the standard sequential short, but you can say, well, you can say, okay, I want this to be executing sequential for some reason. Good. So you can specify that with this parameter. And also you can say, okay, no, I want the sort to be done in parallel. And also you can say, okay, do parallel and also the use vectorization as well. The thing here, because this is a little bit, let's say that we have a library, that in this case STL, and we are giving control to that library. It's a little bit unclear if the thread execution will be like the performance will be the best or not. Why? Because when we call it here, you see that I'm calling here the execution parallel, but here I'm not specifying how many threads I want to use. I'm not specifying about the affinity. Affinity means that, for instance, on ARCHER2 we have 128 cores. Affinity means that the thread 1 is, let's say, tied to the core 1, the thread 2 tied to the core 2, etc. So it's like the one thread is executed all the time in the same core. If we don't specify that, the operating system has a freedom to move the threads between the cores. So for instance, the thread ID 1 could be executed in the core 1, the core 20, the core 50, and also this could not be efficient enough because for memory reasons, because some cores When also a node of ARCHER2 use NUMA, that is a non-uniform memory address. So there are some parts of memory that are easier to get access from the core 1 than from the core 50, for instance. If for some reason the thread moves to the other core, that would be like some performance variations. So this is what is explained here, that you don't have control of the number of threads. It's a little bit you give control to the library. So you may get good performance or may not. So what I say, easy to use, but there is a question in the chat saying, what is the difference between parallel and parallel with the vectorization? Parallel use threads. That's it. Let's say full stop. Parallel with vectorization, the processors, some operations can be vectorized. That means that in the same cycle, in the cycle means in the processor, the operations that does. In the same operation, you can do, for instance, for additions at the same time. So several operations at the same time in the same cycle, but this is allowed by the processor that has this. Parallel with vectorization is like you have two levels of parallelization. The first one is using threads, and inside that thread you can use a vector operation to, for instance, to do the addition of several numbers at the same time in the same CPU cycle. Is that clear? Yeah, that's. Yeah, it's like a two-level parallelization. Okay, so question, C++ threads on OpenMP. Pros and cons, the thing is, because C++, as you can see, there are a lot of standards, C++ 11, 14, 17, 20, 23. Like it seems that, yes, looks like every 3 years there is a new standard. OpenMP has also several standards. There is OpenMP 4.5, 5.0. Normally supports, for instance, the OpenMP 4.5 only supports C++ 98. Let's say the original C++. Let's say this standard that is like an order. And actually, being honest, I'm more familiar with C++ 98. C++ 11 is good because adds a lot of new and good features that could be used. But yeah, I have to admit that I come from C, so C++ and C++ 11 is something that I learned. And actually, yeah, it's good. It gives you a lot of new features and make things easier to code. But okay, coming back about OpenMP, now OpenMP 5.0 supports most of C++ 11, 14. So if you need to bear in mind or be careful, if you want to use something that is implemented, that is defined in the C++ 20, you need to check first if the compiler supports that feature. And also you need to check if, in case that you use OpenMP, if that version of the OpenMP supports this. There are some exceptions, including threads and atomics. You want to, you want to use the latest and greatest, features in C++, OpenMP might not work. Just to keep an eye. The thing is, these new features, in case that are not supported, there is always a workaround. You can always like do something similar. It's like with atomics. For some reason, atomics is not supported. You can always use a lock or a guard lock. So that is always a workaround. So it's not a problem, I would say. It's something to bear in mind and something that you need to be careful with that. Also talking about user features, that's interesting that thread barriers. Okay, that in C++, yeah, I'm trying to get in C++. Seems that well, there are no barriers. Would be likely to be added in the C++ 20. What is a barrier? Is when you create. Imagine that you create 10 threads. A barrier is a synchronization point. So you create 10 threads, and in each thread you specify a barrier, synchronization point. When all threads reach this synchronization point, keeps executing. This is normally done when you use when you need to do update, and you need, for instance, you are updating a matrix, or for some reason you are reading a matrix from a file, and you read the chunks of this matrix, and you cannot work until the whole matrix is loaded to memory or is updated. So there you create a synchronization point. Without a barrier, what you will need to do is like maybe creating and destroying threads. That is also possible, but yeah, OpenMP has a barriers that I remember in C with POSIX threads, I would say that they have barriers, but yeah, it has been like ages since I don't use them. So also back in my PhD times. Also, C++ have a thread pools. Task is a nice feature of OpenMP. Also, you should be careful. Well, it's a note about the task that about the number of tasks that you use OpenMP. If you use a massive amount of tasks, it could not be that efficient for the, because let's say that you have a 1 million task. This 1 million task will be in a queue, so to handle that queue will be quite costly. So you will also, when you use task, be careful about the number of them, that in case that this is like a way too big, will be a little bit of a problem to handle the, let's say, the task queue. I remember use POSIX threads at the beginning in order not to like because we have like I was using them for was a search algorithm. I was using a tree, and to execute this the nodes of a tree of the tree, I was using threads rather than using a task, because the tree was quite big. Also, for parallel for loops, OpenMP is quite good, but well, there is some functionality with the std for each, but OpenMP could be a good solution. Or this is like a vector operations, because it's a SIMD is a single instruction multiple data. So you have, for instance, an addition that the addition is done in parallel for all the elements of the vector. So these are OpenMP features that C++ may have or may not. It's a little bit. So as I said here there is a little bit of this kind of discussion of that. Of course, you can use C++ to build the features that OpenMP may have. But my recommendation or my point of view here is like to try to, if let's say if you want to use a for loop and with OpenMP you can parallelize it easily, yeah, use OpenMP. You can also do it in with the C++. My recommendation is that you should know both choices. You should know C++ threads. You should know OpenMP, and you should choose the one that is more appropriate and the one that, for some reason, gives the best performance. We have said before that also depends on the compiler, depends on the architecture. So maybe you have a machine and you use let's say OpenMP one version and it performs quite well, but maybe you use ARCHER2 and maybe C++ threads works better. It's what is said at the end that the portability and efficiency sometimes is related with the architecture or with the compiler. So there is not like a simple solution that it works everywhere. So you also need to bear in mind that in some cases maybe OpenMP works best for you, the other way around. So you need to have a look at that. What about GPUs? Well, here there are mentioned some C++ frameworks that are Cocos, Gaza, I think, SQL, that you can use for GPUs. Also, OpenMP. I'm aware that OpenMP now implements GPU offloading. So you can. So this is a little bit, and also like this is like not that covering that in this part of the course. Sorry, I see that there is a question in the chat. Usually threads give you concurrency, whereas from example OpenMP gives you parallelism. This is true for C++ as well, threads as well. Yeah, I think that's the point. I think that comes to the answer to your question is like would be maybe this with OpenMP, this line. Yeah, okay, you can see the pointer. This line, they say that this is the timeline. So you are executing your main thread here, and you say, okay, I will create 4 threads. Cool. 4 threads created. Okay, I will, let's say I finish my for loop, and these threads are gone. Okay, so you continue. You can do the same with the OpenMP. This here, I will create 4 threads. Cool. Okay, now I will create 2 more. Fine. I finish with this. I finish. So gives you, okay, you can do see like this. Let's say this is like I would say a more regular pattern. But if you have a more irregular pattern that, for instance, the software of the source code of the tool that I was using for searching was an irregular search. So some regions that were quite big were, let's say, very easy to solve, but other regions, they require more and more and more work. So the search was irregular. Oh, well, this is also mentioned. There are some algorithms that are called irregular algorithms. That means that you cannot predict beforehand the workload of that each part will have. So in this case, for instance, maybe C++ could work better. Or for this pattern, you can also use, but this is like the feature, the OpenMP task. Not sure if this answers your question. So it's a little bit like it depends on the test case that you want to solve. If it's, let's say, regular, if it's a for loop and it's OpenMP is fine, but if in case that you need more, or for instance, when you are, but this is like a more complex, imagine that for some reason you need to implement a server, and you say that each thread handles a request. So with OpenMP, maybe you can create a task, but with C++, you can create the thread with the function that handles the request. It depends on the software that you have to. Okay, there are more differences. The reductions are different in both what I said, that the forking or joining of threads, because also you can have an adaptive, let's say, algorithm that depending of the workload, and also now it's quite a thing about like the energy efficiency, that you see that with the let's say with the 4 threads, it works better than having 8. You can choose okay 4, but yeah, this is also could be also available on OpenMP. It's not clear. This is like a lot of discussion, and if you go on the internet and you imagine in Stack Overflow, there are many threads for this discussion. Threads, yeah, but it's yeah, it's a yeah. Also, again, what they said about the binding threads to sockets and cores, the C++ doesn't contain that. You need to use OS specific functions. I think I remember that with the C and POSIX threads it was possible, but yeah, I'm not entirely sure. But well, here we're talking about C++. So. Okay, so 12:30. So there is a there is an exercise in the repository that talks about threads that you can play with that exercise. But yeah, I'm afraid that this is the end of today's session, and the end of this course. You will receive, if not today, tomorrow, an email with a feedback form. We will appreciate if you can. It's pretty short. It will not take more than a few minutes. If you can tell us how did you find the course, and if you have any suggestions of how we can improve the course, or things that you would like to learn, etc., please fill in the feedback. We will appreciate your answers and your feedback on this. Again, if you have any questions, please feel free to write them in the search bar or send us an email. Also, you can use support at archer2.ac.uk. C++ is quite let's say, a big language, and was not possible to cover everything. So again, you have something that has not been covered, you want to know more about that, or please contact us, and we will be more than happy to keep in touch and help you with this C++ journey. Okay, so I stop talking. Hope you have a nice rest of the day. Many thanks for joining the course, and also thanks to Joseph today and the rest of the instructors. Thank you for attending, and that's I'll stop talking. Have a nice rest of the day, and hopefully see you in future courses. Bye for now.